Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin the second application of derivatives of a function, and that is from the geometric point of view to deal with tangents and normals. Before that, let's look at the concept of increasing and decreasing functions. So if you look at the graph of a function, I'll just draw some graphs first. Say one is like this, the other is like this, right? So these are just four functions. Now this function, you can see that as the value of x goes up, the value of y goes up, right? So this function is what we would call a strictly increasing function, right? So there's a difference between the two. It's possible for y to increase as x increases or for it to stay constant, right? So we say that if it does not stay constant, then we'll call it a strictly increasing function. If there are regions where y is constant as x increases, then we'll just call it an increasing function. So to be strictly increasing is a stronger condition than to be increasing, right? Similarly, this would be a decreasing function, and a function like this would be a strictly decreasing, because in this region y is constant with respect to x, and generally a function does not need to always be increasing or decreasing. This is a mixed function. In this region, the function is increasing. In this region, it's decreasing. In near this region, it's probably constant. So it can be a mixture of all of them. Right. So let's give us the proper definition of these. If f is defined in a domain, let's say a to b, a and b both are included, then f is called increasing. If I'll just write all four conditions. Yeah, so let's start with strictly increasing. Strictly increasing was a function in which as x increased, y increased. There was no constancy, no decreasing. As x increased, y increased. That means for all x2 greater than x1, f of x2 should be greater than f of x1, where x2 and x1 both belong in this interval, right? So every x2 which is greater than x1 will have a y which is greater than the value of y at x1. It is increasing if, now you can just, from this you can see the definition here for x1 and x2. For the sake of completeness, I'll just write here in a comma b, but that applies for all four of them. F of x2 is either greater than or it is equal to f of x1. If it is equal to at some places, we still call it an increasing function. A strictly increasing function is one in which f of x2 can never be equal to f of x1. Decreasing if, sorry, this is for all x1 less than x2, or I'll just write x2 greater than x1. So they both need to belong to a comma b, but also the other condition is x2 is greater than x1. For all x2 greater than x1, f of x2 less than equal to f of x1, and strictly decreasing if for all x2 greater than x1, f of x2 is less than f of x1. Right. So these are the four conditions for a function to be increasing, strictly increasing, and so on. Now this is in a region. We can actually talk about whether or not a function is increasing or strictly increasing or decreasing or strictly decreasing at a point as well. So if you just look at a graph, right, what is the function at this point? Is it increasing, strictly increasing, decreasing, strictly decreasing? Well, and just let's look at a region here as well where it might be constant. Right. Now this is a mixed function. Within this region it's increasing, this region is constant, this region is decreasing, and so on, right? So a function is increasing at a point if you can find an interval in which it is increasing. The definition is that simple, but it says if you can find an interval, because any one interval will do. If you take this big interval, this interval is still around this point, right? But in this interval the function is neither increasing nor decreasing. So you shrink the size of your interval, you make it smaller. And if you keep making your interval smaller, because otherwise you could have a function like this, very fast varying also. but you look at a particular point, it says if you keep decreasing the interval, if you can even find any one interval in which the function is increasing in that interval, then the function is increasing at that point. If you can find any one interval in which it's decreasing, then it's decreasing at that point. See, you can never find an interval around this where the function is decreasing. It will either be mixed or increasing, right? So at this point the function is increasing. Now we can use a theorem we learned at the end of the differentiability video, the mean value theorem, to actually prove something which tells us whether or not functions are increasing, decreasing or constant. So we'll write that theorem. If f dash of x is equal to dy by dx and f is defined in a to b, then f is increases if and constant. So it is increasing if f dash of x, the derivative, is greater than 0 for all x between a and b. So if f is defined in a region and the derivative of f is positive every interval in that region, then the function is increasing in that interval between a comma b, right? It is decreasing if f dash x is less than 0 for all x between a and b. Now remember, it's for all x. If you can find some x where it's greater than 0, some x where it's less than 0, then in the whole interval the function is neither increasing or decreasing. It's a mixed function. But if during an interval, if you can find f dash x is positive during the whole interval, then it has to be increasing. You can find f dash x is negative, then it has to be decreasing. I'll not write the ones for strictly, but if f dash x is greater than equal to 0, then it's strictly increasing. If f dash x is less than equal to 0, it's strictly decreasing, right? So it is constant if f dash of x is equal to 0 for all x between a and b. If f dash x is 0, then it is constant. Now I'll just prove the first part, and you can easily see second and third parts from the proof. The proof is the mean value theorem, which says that we can always find a c. We can find a point c in a comma b. If you don't remember this theorem, you can watch the differentiability video again. We can find a point c in a comma b such that f dash of c is equal to f of b minus f of a by b minus a, right? So now if we have let's say this number line, this is a, this is b, this is c, so we can find a point c between them such that this statement is true. But this is also valid for any x1 and x2. Let's say this is x1 and this is x2, such that x2 is greater than x1. Then we can find, let's say, a point D in x1 and x2 such that this is true for this point. So f dash of D is equal to f of x2 minus f of x1 by x2 minus x1. This is true for all points x1 and x2, right? Now, between a and b, if f dash x is always positive, that means f dash d is positive. And since x2 is greater than x1, that means f of x2 is greater than f of x1. F dash of d greater than 0 implies f of x2 is greater than f of x1, which means it is an increasing function. If f dash x is negative for all x between a and b, then you take any x1, x2 between a and b, you'll find a point D such that f dash d satisfies this. x2 is greater than x1, this whole thing is negative, so obviously f of x2 is less than f of x1, which makes it a decreasing function. And if f dash x is 0, that means f dash d is 0, which means f of x2 is equal to f of x1. So fx is a constant function because f of x1 is equal to f of x2 for all x1 and x2 between a and b. So it's a constant function. Let's move on to the actual topic of this video now, tangents and normals. We saw tangents briefly in class 11th when we studied differentiation, but let's look at this stuff in a little bit more detail now. Let's say we have a function y of x and we have a graph of it, and let's say this length is delta x, this is x, this is y, this is delta x, and this is delta y. So this is y plus delta y and x plus delta x. So dy by dx, what is that? It is limit delta x goes to 0, delta y by delta x, right? Delta y will be f of x plus delta x minus f of x, right? And as y goes to x, we can see that delta y by delta x will become tan theta, where theta is measured at the point where we are calculating the derivative. Usually it would be 2 points, but as delta x goes to 0, this point approaches this point. So, excuse me. So we know the derivative of y with respect to x will be tan theta, where theta is the angle made by the tangent with the x-axis. Right. It is also referred to as m, or the slope. And this is a general concept in coordinate geometry for any line. The slope of any line is tan theta, where theta is the angle made by that line and the positive x-axis. And dy by dx is tan theta, which is the slope. Now, there are some special cases. When the line is parallel to the x-axis, the slope is 0. Right? Because tan theta will be 0 because theta is 0. But this means dy by dx is 0, which is something we already know, because for a constant function dy by dx is 0. Right? Also, when a line is parallel to the y-axis, the angle made by the x-axis is 90 degrees. Tan 90 is infinity. So, as the line becomes vertical, m goes to infinity. Right. At 90 degree, m will be infinity, but in mathematics, we do not like to say the value of something is infinity, so we say that it goes to infinity. Right. So this is a very simple way of calculating the slope of the curve at a particular point. That will simply be dy by dx. So let's say this is the curve for the function y is equal to 3x cubed plus 2x. And we are asked to find the slope of this curve at x is equal to 2. Well, the slope will be nothing but dy by dx. So what is dy by dx here? It will be 6x squared plus 2. Now this gives us the slope as a function of x. At x is equal to 2, the slope will be 6 times 4 plus 2, that is 26. Right. So in this way, you can calculate the slope at any point. Now the other thing is normals, and the normal is simply the perpendicular to the tangent at any point. So if this is a curve, then at this point, this is the tangent, right? Perpendicular to that, at the point perpendicular to that, this will be the normal, right? This is, let's say, the tangent t, this is the normal n, right? So at any point, you can get the tangent that will have the slope equal to the derivative, and you can get the normal. What is the slope of the normal? Let's say the slope of the tangent is m, and the slope of the normal is m dash. Okay, then we know that if theta is the angle made by t, then 90 plus theta will be the angle made by n, right, with the x-axis. This is the positive x-axis, this is theta, this is 90, so this is 90 plus theta. In other words, if you take the angles and you find the difference between them, that will be 90 degree, right? So let's say m makes theta 1, so m will be tan of theta 1. M dash makes theta 2 with the x-axis, to it will be tan of theta 2. And we know that theta 2 is equal to theta 1 plus 90 degrees, implies theta 2 minus theta 1 is equal to 90. Now we know the formula for tan of a plus b. In this case we need tan of a minus b, and that is tan a plus tan b, tan a minus tan b by 1 plus tan a tan b. This is the formula for tan of a minus b. If the difference of a minus b or theta 2 minus theta 1 is 90 degrees, that means if a minus b is equal to 90 degrees, that means this term is infinity. That means the denominator is 0. That means tan a tan b is equal to minus 1. And tan a is the slope m, tan b is the slope m dash. So we get the relation m dash is equal to minus 1. Or m dash is equal to minus 1 by m. So if the slope is 1, or the slope of the tangent is 1, the slope of the normal will be minus 1. The slope of the tangent is 10, the slope of the normal will be minus 1 by 10. The product of the slope of the normal and the slope of the tangent will always be minus 1. Right. One final thing, with this we can just simply find the slope of the normal or the tangent at a particular point. How do you actually find the value? How do you actually find the equation of the normal or the tangent? Right, so that's a more general concept, that is to find a line, to find the line rather, with slope m and passing through say x0 comma y0. Right, so if we need to find the equation of the line that has a slope m and passes through x0 comma y0, that's a very standard formula. Let's say this is the line L, then obviously this angle will be theta and m will be tan theta. This point is x0 comma y0. Let's take any general point on the line x comma y. It could be in this direction or in this direction as well. We know that this angle is theta. That means we know that m, which is tan theta, is y minus y0 by x minus x0. If we took it here, it would be y0 minus y by x0 minus x, but it will still, both of them will be negative, so this will still be the formula that applies. This basically gives us the equation of the line. The equation of the line is y minus y0 is equal to m times x minus x0. This is our final answer. The equation of a line that has a slope m and passes through x0 and y0. What is the equation of a line that has slope minus 1 by m and passes through x0 comma y0? That will simply be y minus y0 is equal to minus 1 by m times x minus x0. The slope is minus 1 by m. If m is the slope of the tangent, then this is the equation of the tangent for the point x0, y0, and this is the equation of the normal for the point x0, y0. Right. Let's look at a few examples. Let's say y is equal to, let's take a simple case initially, y is equal to x squared. We know the graph of y is equal to x squared. It goes something like this. Let's take the point 2. So x is 2, y will be 4. Right. So let's take x0 is equal to 2, y0 is equal to 4. At this point, obviously, this curve will have a tangent and this curve will have a normal. Our aim is to find the equation for the tangent and the normal. Right. So first we'll find dy by dx, that is 2x, that is equal to 4 at x0 is equal to 2. So the slope of the tangent, we'll just call it m, is 4. What is the slope of the normal? That will be minus 1 by m, that will be minus 1 by 4, because their product has to be minus 1. And this point is 2 comma 4. Now you can easily find the equation of the tangent. That will be y minus y0, this is 4, sorry, y minus y0 or y minus 4 is equal to m, which is 4, times x minus 2. Or what you get is y minus 4x, this is minus 4, this is minus 8, so plus 4 is equal to 0. This is the equation of the tangent. Let's verify that it does pass through 2 comma 4. If x is 2, then this is minus 8 plus 4 is minus 4 plus 4 is 0. So it does pass through 2 comma 4 and it does have a slope dy by dx is equal to 4. What is the slope of the normal? That is also quite simple. Y minus 4 is equal to minus 1 by 4 times x minus 2, which gives me 4y plus x, and then you'll have minus 16 and 2, so minus 18 is equal to 0. This is the slope of the normal. You can verify that it also passes through 2 comma 4. When x is 2, we have 2 minus 18, which is minus 16, and 4y is 16. So this is how, using if you have the formula for any function, you can calculate the slope of the tangent and the normal. Now here we can add one more concept which we learned in the video of differentiability. We do not always need to be given the explicit formula for the function. Sometimes we can be given an implicit relation for the function, which means a relation between x and y, and we learned in the video of differentiability how to calculate dy by dx for such an equation. So let's look at an example like that. Let's say we are given the relation x squared by 4 plus y squared by 9 is equal to 2. We'll see this sort of curve when we get to the video on conic sections or geometry, coordinate geometry, but this is basically the curve of an ellipse. It looks something like this. It's sort of like a flattened out circle. Right. So right now we don't need to worry about that. Right now this is what we are given. This basically tells that for a value of y, you will have 1, or in this special case 2, values of x. So this is basically y as a function of x. And you can get the value of dy by dx by differentiating this implicitly. So what you'll do is d of x square by 4 plus y square by 9 by dx is equal to d of 2 by dx, which is 0. This will give me d of x square is 2x. So 2x by 4 plus d of y square by dx, and you'll have 1 by 9 here. And d of y square by dx, you can write it as a chain rule. You can say d of y square by dy into dy by dx. So what you'll get is 2x by 4 plus this will be 2y dy by dx. So 2y by 9 dy by dx is equal to 0. So what we get is dy by dx is equal to minus 9x by 4y. Right. Now let's say we want to calculate the equation of the normal at 2, 3. 2, 3 does pass through this ellipse, and we want to find the equation of the normal at 2, 3. Well, first we'll find the slope of the tangent at 2, 3. So dy by dx is the slope of the tangent at 2, 3, or m, and that is equal to minus 9 into 2 by 4 into 3, 2, which gives us minus 3 by 2, which means that the slope of the normal m dash will be 2 by 3. And we can now directly find the equation of the normal. Y minus y naught, which is 3, is equal to 2 by 3 times x minus x naught, which is 2, which gives us 3y minus 2x. This is minus 9 plus 4 is minus 5 is equal to 0. So this is the equation of the normal to this curve. This will be a point 2, 3. This is the tangent. This is the normal. So we have found the equation to the normal of a curve at a particular point. Right. Now you don't just need to be always asked this explicitly. They can give you a function, say y is equal to x squared plus y is equal to x cubed plus 9x minus 9x, say. They could give you y is equal to x cube minus 9x and say where is the tangent parallel to the x-axis. So a line parallel to the x-axis will have the slope 0. We already discussed that. So dy by dx will be 3x squared minus 9. That needs to be 0. That means at x is equal to plus minus root 3, this tangent will be parallel to the x-axis. Right? They could give you a function and say find the tangent. For example, they could give you y is equal to x squared plus 6y plus 9 and say find the equation of the tangent or the normal, let's say the normal, where y cuts the x-axis. These are just different words to give you different conditions, mathematical conditions. Y cuts the x-axis simply means that the value of y is 0. So you just take this to be 0, you say x squared plus 6y, this should be 6x, sorry. X squared plus 6x plus 9 is equal to 0, which gives you x plus 3 whole squared is equal to 0, which means x is minus 3. So you find x is minus 3. So what is y? That is 0. So minus 3 comma 0 is the point. Now that you have the point, you can get dy by dx, which will be 2x plus 6, and then you can get the value of dy by dx at a particular point, and then you can find the slope and the normal. Right? So dy by dx is 2x plus 6, that will be 0. From that you can find the normal and so on. Right? So these are different ways in which you can be asked to find either the equation of the tangent or the slope of the tangent, or the equation of the normal or the slope of the normal at a particular point. This completes the geometrical applications of derivatives, which is to see whether a function is increasing or decreasing or constant, or strictly increasing or strictly decreasing, and then to find the equation for tangents and normals at particular points. In the next video, we'll look at the final application of derivatives to find the maximum or minimum value of functions. Thank you.